Welcome to lecture 22. In the last lecture, we have derived an expression for U as degree of consolidation. Please remember the definition is equal to settlement at any time divided by settlement at infinite time, or we can say SD by S final. And the solution is U is equal to 1 minus sigma I going from 0 to infinity 2 by m square e to the power of minus m square t. But you don't have to remember all that. Much easier to remember U is equal to 2 root t by pi. We said that when you plot on a square root of time plot, you get a straight line. So U is proportional to square root of time for U less than 60%. And it's equal to 1 minus 8 by pi square e to the power of minus pi square by 4 into time factor t. What does it mean? It means I only have taken the first term when I is equal to 0, then m is equal to 1, so I get pi square by 4, it becomes 8 by pi square, and m square is pi square by 4. So the exponential term becomes negligibly small. So see, please remember that t greater than 60%, we need to take only one term of the exponential 1, and in case U is less than 60%, it's proportional to square root of time t. We also found out that CV can be calculated by either of the methods, 848 h square by t90, or is equal to 0.197 h square by t50. From the Taylor's method and from the Casagrande method, you can determine. Just to give you a feel, CV usually is between 1 to 3 meter square per year. Or if you look in terms of centimeter square, it could be the order of 10 to the power minus 3, 10 to the power minus 4 centimeters per second. Another very important thing I want you to notice, why does it take such a long time? If I look at t is equal to CVT by h square, in the laboratory h is 10 millimeters, which is equal to say 0.1 meter. In the field, h can be, let's say, maybe 8 meters. So let us try to find out how long will it take to consolidate. In the laboratory, I need only, let us say, maybe 4 hours to get 90% degree of consolidation. So T90, which is 848 CV, T90 by lab is 0.1 meter square. So for whatever CV, T90 is equal to 848 into 0.1 square by CV. In the field, for the same soil, if the thickness is 8 meters now, T90 in the field is equal to 848. If the thickness is 8 meters, I need 4 meters as the maximum drainage path. So 4 square by CV. Now you can say the field time is equal to is T90 in the lab. So let's say lab would be T90 field by T90 lab is 4 divided by 0.1 square. Am I right? I need 4 square and 0.1 square. This is 16 divided by 1 into 10 to the power of minus 4. So this becomes 16 into 10 to the power of 4. So in the field, you need something like 16,000 more time than in the lab. So what took us 4 hours may take 10, 20, 50 years in the field. And that is the main problem with soft clays. You construct something today, the settlements keep continuing for 5, 10, 15, 20 years, depending on the value of CV and depending on the thickness of the layer. And it's a very slow process and can go on for a very long time. And this is how we try to estimate how much time is needed for 50% or 90% degree of consolidation. One major correction we had to do would be, we are not going to apply the load all in one day. Please remember, we said it's a monotonic loading. Q, Staggered solution is valid monotonic loading, which means all the load is applied at t is equal to 0. As if you suddenly put the building or the embankment or whatever load on the ground. It doesn't happen that way. Usually we go through a period of construction. Maybe usually most projects in India, whether it's highway, liquid storage tank, building, etc., take to 2 to 3 years. So maybe it will go on like this. So this is the final T naught. It's, you can say, time for end of construction. What happened? In the first year, you have constructed, the rains came, the monsoon, just like what it is. Next year again it goes up, there is a delay, and finally it gets done after maybe 30 months, 40 months, etc. In a more refined one, you can actually consider each of them. As a simple measure, I would say let us take a linear increase. This is, so say this is equal to some 30 months. The project completion is 30 months. So the load is gradually applied over a period of 30 months, from 0 to 30 months. And we say this is the rate of loading, and you can, if you call it as R, is Q by T naught. Whatever load you have applied, let us say this is equal to maybe 100 kPa. So 100 kPa by 30 months, so it becomes 3.33 kPa per month. How do you estimate the settlement, particularly at the end of construction? You have finished the project. Do you think it will be completion, consolidation is over, or only partial? So to estimate that, we have what is called as correction for end of construction. This is called construction loading. Please remember, we have approximated by a straight line. That is, the load is applied like a ramp gradually. So what we do now is, first, I predict settlement at any time t using the Staggered theory. I say that ST is equal to S final into degree of consolidation. S final is M sub V into Q into 2H, what is the thickness. U is the degree of consolidation. U is a function of time t. How do I get it? If I know t, I calculate time factor CVT by H square. So I can substitute, I know the property of the soil, I know the maximum length of the drainage path. I said t is equal to 1 month, 2 months, 5 months, 12 months, etc. I will get, assuming the load is applied, this is settlement with t for monotonic loading, monotonic, corresponding to AB. Whereas you would like to know for CDB, which is increasing gradually. This is assuming as if the load is applied at t is equal to 0. We know the property of the soil, the compressibility in terms of coefficient of volume change, the applied stress, and the thickness of the layer. That gives me the final settlement into degree of consolidation as a function of time t, or you can even put as a function of time factor t. You have derived the equation, so you know ut as a function of time factor t. I have given the expression just now, so you know how to estimate that. I take t is equal to, let's say, 1 month, 3 months, 6, 12, 18, 24, 30, etc. I can substitute here and get the time factor. If I get the time factor, I know the degree of consolidation. I multiply the final settlement with degree of consolidation. I get the settlement at any time t. But I would like to know what is the real settlement at the end of construction. You agree that it took us 30 months for the construction load to be applied, and it is gradual. Can I say that it's approximately equal to half the time, that is 15 months for the full load. Load increases from 0 to 100% in 30 months. right? Is it approximately equal to average load, or I'm sorry, the load applied over half the time? Full load, which is equal to 30 by 2. What we have said is, instead of the load increasing from 0 to 100%, it's going to be applied from T0 by 2, full load acting at half the time. So this is one simple approximation we make. As engineers, we always approximate so that we get a simple solution. So what if I want to find out settlement at T is equal to 30 months? I'll find out settlement at T is equal to T0 by 2, and that I transfer here. Whatever settlement occurs in half the time of construction will be the settlement at the end of construction due to gradual application of load. The difference is, this plot is assuming all the load is applied at T is equal to 0, but now you are calculating settlement assuming the load is applied at average time, which is 0 to 30 months, which is 15 months. So I take T0 is equal to T is equal to T0 by 2, and I get that settlement. I transfer it here. Suppose I wanted something like, say, 48 months. Then I'll say, what is the time from here? This is 15 plus 18. So this becomes total 33 months. I'll look at it, 33 months, and I transfer it here. Sorry, where is it? Here. I wanted 48 months, but 48 means I have 15 months corresponding to average of construction time plus 18, 33. I get this. If I wanted 60, 15 plus 30, which is 45, I come back here, transfer it. So we'll now say the corrected for construction time. We as civil engineers cannot put all the load in one go. So we say we are building it gradually, and we say if I am applying load over a period of 24 months, it's equivalent to all the load being applied over half the period. That's all the approximation we make. It's increasing from 0 to 100% over a period of time. I say half the time full load is acting. Gradual, X amount, and X time, and full load half the time. So once you say I'm reducing it here, similarly I do a bit of correction here, and we are not particularly keen on what's happening before the end of construction, but we are interested in how much settlement is going to occur after you finish the construction. And you can see that predicting as if the whole load is applied, if I predict applying the correction, it will be something like 70–80%. And whatever happens will be delayed. But finally, as T tends to infinity, it does not matter. Both the curves converge. This is for monotonic loading, and the other curve is for construction loading. Please remember, the method is very simple. If I want to know how much settlement occurs due to construction loading at the end of 30 months, I take how much settlement has occurred after 15 months, and that I transfer to 30. If I want after 48 months, then I say first 30 months corresponds to 15, and 30 to 48 is 18. I take 33 months, and I transfer it here. If I want at the end of 60 months, 30 means 15 plus another 30, it becomes 45. So I take the point corresponding to 45 months, I transfer it. And these points are combined to get the application of, the prediction of settlement due to construction loading. The second important parameter is settlements in the field take very long time to attain the final values. What is a long time? It could be 10 to 50 years. Now nobody can wait that long to use the building or the structure. Is there a way in which we can accelerate these settlements? So what are the methods of accelerating? What we do here is the ground. Normally the flow is vertical and the thickness is very large. H can be, as I said, 5 to let's say 16 meters. Is there a way in which I can reduce the drainage path? So what we do is, let us say we drive a hole fill it with sand. They were originally called sand drains, and they were installed at a spacing of something like 2 meters to 3 meters. That means if I have a large ground, I can install these drains, let us say at a regular spacing of say 2.5 meters. This is what is called as a square pattern. We can also install them in what is called as a triangular or staggered pattern. Same area, let us say this is some 100 meters by 100 meters. I can install drains in a staggered fashion, and the spacing is the same between any two adjacent drains. So I call that as S. Even here I call it as S. In case of square pattern, it's two perpendicular directions. In the case of triangular or what they call as staggered pattern, the spacing is the same between any two adjacent near one. The spacing between this drain and this drain is S, which is 2.5 say. Similarly, this drain and this drain, 1, 2, 3. Between 1 and 2, 2 and 3, 3 and 1, it's exactly the same. In this case, 1, 2, 3, 4. Between 1 and 2, 2 and 3, 3 and 4, 4 and 1 is exactly the same spacing. If you do that, and we have these drains, earlier they were all made as a hole of 0.3 meter diameter and fill it with sand. Fortunately now we have what is called as prefabricated vertical drains. Usually they are about 100 millimeter by 4 millimeters. These used to take 1 hour, 2 hours to install each one. Whereas this one is like your sewing machine, you can stitch it, push it into the ground. Usually it takes maximum 2 minutes for a 10 meter long pipe. This is, let's say, 10 meters. I can simply push it inside using a small mandrel, and now they have become very popular. So what happens is the water doesn't have to flow to the top or bottom. I have a pervious drain within the soil. So the maximum distance it has to travel is half the spacing. Basically, if this is the spacing S, if there is a water molecule here, will it go to the top or would it try to go to the drain sideways, which is at a smaller distance? You know that water always takes the line of least resistance, so it will now flow horizontally into the drain. And how does it happen? Now if I have the square pattern, I draw the symmetry and I get a square. This plane is halfway between these two, so water here will go to the left and molecule to the right will go right. Similarly, top, bottom. So the zone of influence is a square. In this case, the zone of influence is a hexagon, and we convert them into an equivalent circle. If you do that, the diameter of the equivalent circle is equal to 1.13 times the spacing per square pattern and is equal to 1.05 times S for triangular pattern, which means all the water within that cylinder will flow towards the drain and not to the top. Maybe a little bit from the ends, but 99% or 95% will flow horizontally. So the flow now is horizontal, and if I now look at the zone of influence, this is the drain, this diameter is dE, and this is the diameter of the well or drain, dW. The flow is now radial. All the flow takes place horizontally. What we have done is two very interesting things. One is reduce the length of the drainage path. Instead of 8 meters or 7 meters, it hardly 1 meter. And you have seen that time factor when you look at it, it's proportional to, inversely proportional to the length of the drainage path, square of the drainage path. So if I just reduce it by from 5 to 1, you have reduced the time by 1/25. Second thing would be, we have discussed earlier, permeability in the horizontal direction is generally greater than permeability in the vertical direction. The flow is much easier and faster, so you can, what is taking 10 years, you can finish in maybe 6 months, 40 days, 50 days, etc. So we need to solve the problem of what you can call radial consolidation, which is, if you remember, we wrote for vertical consolidation, for radial flow, the pore pressure dissipates CV, I'll put radial, into, again from your calculus and algebra, you can do this transformation from Cartesian to cylindrical coordinate system, and you can prove that very easily that the governing continuity equation gets changed into this case. That is, derivative of u with respect to time is equal to CV in the radial direction. What will that be? CVR is K in the radial direction by MV into gamma W. Please note that the flow is radial, but the compression is vertical. So I still need the same coefficient of volume change, and I get this expression. What are the initial and boundary conditions? U is equal to U naught at T is equal to 0. And here, if I take the radius, R is equal to dW by 2. That is the radius of the well. U is 0. It is pervious. And R is equal to the radius of the zone of influence. There is no flow across that. If I take the boundary, can there be any flow across that? All we said was the flow is towards the well, so there will be no flow across, which means the gradient there is 0. So these are the initial conditions, and these are the two boundary conditions. We have a very interesting problem with respect to strains. If I now look at a simple unit cell, that is, I have a drain here and the zone of influence, and on top I am applying the load. We said this point, this is the drain, diameter of the well or drain, and this is the diameter of the zone of influence. As we apply the load Q, the consolidation will be very high here from T is equal to 0, because this is very close to the drainage boundary. So we have a situation where the settlements can be more at the drain and less far away, because it will take time for the pore pressure to travel from here to here. This is called a free strain case. But fortunately, on every soft clay, we are going to put in a granular mat, which leads to what is called as constant or equal strain. That means the whole thing will settle uniformly. And the solution for this is very easy. 1 by 1 minus e to the power of 8 TR by Fn. Very simple expression. I think I'll give the next time too. Where Fn is equal to natural log of n minus 3/4 times n, where n is equal to d by dw. It's a very simple expression for degree of consolidation due to radial flow. U is equal to 1 minus e to the power of minus 8 time factor TR. TR is equal to CVR by T into d square. What is that? Time factor for radial consolidation, coefficient of consolidation for radial flow, into time divided by d square, which is the diameter of the unit cell or the diameter of the zone of influence. And if you now calculate, you can see that d is a very small term, and this is a very fast decaying term, and you can get the degree of consolidation to be very fast. If I plot UR versus log TR, maybe for us to get 90%, we had 848. You will find that 90% or something like that can be obtained even with 0.1. The consolidation is very fast at a very small time factor, and so what was taking for T90 maybe 10 years, T90 with radial flow will become hardly maybe 90 to 120 days. So what we do in the field is we go there, use this equipment to push it inside the ground and install the drains at regular interval of maybe 1 meter, 1.5 meters, 2 meters. You as an engineer will design the spacing as the time required. Somebody says, I have this refinery coming, I have this port coming, I have an embankment coming. I want to finish the construction within 9 months, 6 months, 12 months. You take that, find out how much settlement degree of consolidation you want to achieve, decide the spacing. If I finalize the spacing, I can get DE, and from DE, I'll get the time factor T, and from time factor T, I get the degree of consolidation. Or you can work back to using this equation very easily without any problem and design the vertical drains. This is one of the most popular methods of improving ground, soft ground, so that you get a very fast consolidation. One more parameter we haven't discussed yet is what is called as secondary compression. If you remember, we said that if you plot settlement as a function of time t on a log scale, say in hours or something like that, this is 0, let's say maybe 2 mm in the lab, the pore pressure here is 0, which means we said 100% primary consolidation. At t is equal to 0, u is equal to u naught, which is equal to applied load. At t corresponding to T100, u is equal to 0, which means all the pore pressure got dissipated. But the soil continues to deform, and so we call that anything after the primary as secondary compression. In geotechnical engineering, soil mechanics, we call it secondary compression. In engineering mechanics or other materials, we call it as creep. Most materials creep, that means they continue to deform under constant load. So creep is deformation under constant load. Here secondary compression is deformation under constant effective stress. So you have applied, let us say Q is equal to 100 kPa, sigma prime is 0 because all the load has gone to the pore pressure. But after 1 day in the lab, or after maybe 10 years or 1 year or 5 years, whatever it is, the pore pressure is 0, which means the effective stress is equal to Q. Because pore pressure is 0, all the applied load goes to effective stress. So now whatever deformation you get under constant effective stress, we call it secondary compression, and this continues for maybe 10 years, 50 years, 100 years. So what we say is, let us take the slope of that. We define C alpha as the coefficient of secondary compression. It's equal to delta delta per log cycle of time. That is, I may say compression, it could be say 100 minutes to 1000 minutes, 1 hour to 10 hours, 1 week to 10 weeks, 1 month to 10 months. This is one log cycle, or 1 year to 10 years. And we define that or determine from the experiment. We look at the slope for 1 log cycle, how much compression takes place. That is defined as the coefficient of secondary compression. This is the other parameter we need to determine from the odometer test. So we can determine coefficient of consolidation, we can determine E log P, of course, and compressibility, and the coefficient of secondary compression. And we use this to predict settlements, which we'll take up in the next class.